In the last two examples, example 4 and 5 of this section, I really want to hone in on the difference between growing and decaying, or curving up and curving down. Okay, so let's look at decay. Suppose y equals 4 times 1/2 x to the x, I'm sorry, 4 times 1/2 raised to the x exponent. Fill in the table of values, then graph. Okay, so that means that it's halving every time. So if we notice, it's half of 4 is 2, half of 2 is 1, half of 1 is a half, half of a half is a quarter, half of a quarter is an eighth. But then we would be doing the reverse of that. So we're actually doubling if we go up the chart. So double that is 8, double 8 is 16, double 16 is 32. Graph this function. Well, notice that all of these are positive. So I'm going to do the thing where I'm like, who cares about this negative space? So let's just move it down and say, here is where my x-axis is going to be, because there is no negativity in this one for y values. Okay, so let's plot 0, 4, and I'm just going to count by ones. So, let's see. I mean, hold on. That goes up to 32, and I only need to. I'm going to go with this. So I'm going to make this be 1, 2, 3. And -1, -2, -3. So I have space to expand that out, perhaps. And then, do I need to count by 2? So you have to. I feel like I don't absolutely have to count that. Let's see. How many is this? 1, 2, 3, 4, 5, 6, 7. It's like 4. Let's just keep it counting by 1. So that means that this would be 1, 2, 3, 4, 5. 6, 7, 8, 9, 10, 11, 12, 13, 14, just so that we have a clear idea. Okay, 0, 4. 1, 2, 3, 4. 1 to the right, 2 up. Got it. 2 to the right, 1 up. Done. 3 to the right, half up. Sure. 4 to the right, quarter. Let's see. 1 to the left, 8 up. 1 to the left. 1, 2, 3, 4, 5, 6, 7, 8 up. 2 to the left, 16 up. So this was 14 up and 2 more. Yeah. Okay, I see the swoop. It looks like a slide. Sliding down. Here we go. Okay, and these fractions, again, they're not negative. So there is our curve. Sweet. As the x's get more and more negative, what happens to the y values? Oh, they're getting huge, right? So the more negative this becomes, the bigger these are getting. Let's write that. As x get more negative, the y's get larger quickly, I would say. I mean, they skyrocket. Let's say quickly. Yeah, they get big. Okay. Will there ever be an x value that gets us a y value of 0? So we are getting smaller and smaller fractions here, but none of them are negative and none of them are actually going to be 0 because we just keep taking half. And it's, I mean, even though we are taking half of small things, it'll still be non-zero. So here's what I mean. We're taking half of stuff. So 1 divided by, so this pattern as I see it, 1 divided by a big number still will never equal 0. Just won't. Okay. Here, I don't know. Should be happy. Just meh. All right. And so we definitely have this boundary happening. There is that boundary. Okay. So remarks. What is remarkable? Number 1, so this I want to just kind of zero in on the difference between these graphs and the inverse, which also have curvature. So exponential graph images have a horizontal asymptote, aka boundary. Okay. When it comes to the inverse models, right? Inverse is also curved, so inverse variation models also curve, but have 2 asymptotes. Okay. Whereas this one, it's just going to keep going over here. It never, it wasn't pushed like, no, you get back over there. No, go get over there. No, it's going to keep going like it wants. It doesn't have another boundary. The only boundary that it has is here. That river is flowing and it is not going to erode whatever's there. Okay. And what else do I want to say? Yes. Another difference is their pattern, right? So here's what I mean. Exponentials have a constant multiplier, constant ratio, but inverse variation models, they have the constant K. They do not have that. I always think that constant K. Exponential growth versus exponential decay. So now, I wanted to talk about this curvature, right? Like the difference between having 2 boundaries and 1. So here's what I mean. Inverse variation from section 4.4, exponential, 2 boundaries, 1 boundary. Okay. But I also want, so in addition to that, I also want us to take a peek at the difference between, where did we have growth? We had some growth like this one versus that one. These are both 2 exponentials. This one came from example 3, where it was tripling every time, so growing, like the bacteria model. And this one was an exponential model where it was taking half of it every time. So this one was tripling, so going up, and this one was multiplying by a half, so coming down. They both have 1 boundary, and they're both exponential because it's repeated multiplication. But I want us to compare those two, like which one is growing and which one is coming down or decaying. So with exponential growth, the graphs or the pattern, the graphs response output or y values go up, aka increase, as the explanatory variable x values also increase. Going to the right. And exponential growth, so in this model, where we have a times b to the x, this value right here, the constant multiplier, is bigger than 1. Constant multiplier bigger than 1. You know, doubling, tripling, making it go up 1.5 times, all of those, and say, okay, well, if I'm doubling, I'm growing. If I'm tripling, I'm growing. If I have 1.5, well, that's still growth, you know, after every time, as opposed to decay, where I'm portioning and portioning and portioning. So when it comes to decay, what I think about there is the graph's response, aka dependent, aka y. The graph's response goes down, responses down as the explanatory variable increases. Explanatory x values are increasing. Yeah, it's going down. Yeah. So here, in this case, it was going down by 1/2 every time. So as 1 is going up, as these x values are going up, these y values or these outputs are coming down. Reminds me of the inverse, which is why I wanted to make sure we're crystal clear on their differences. But here, like in the case with 1/2 and 1/2 and 1/2, or even the caffeine, where it was 0.8, 0.8, 0.8, which is 8/10, that is a constant multiplier that is a fraction. So this one is a constant multiplier, is a fraction, or decimal, same, between 0 and 1. So 1/2, 1/3, 1/4, 0.8. So that's the big difference between exponential growth and decay. It's just this number, the constant multiplier, that's different. But they both still have just one boundary. All right, so let's do an application. Suppose the price of a video game is given by the equation P of M is equal to 40 times 1/2 to the M, where M represents the number of months the game has been on the market. Fill in the values. Okay, so this, I'm actually gonna practice using my calculator as well. So 40 parentheses times 1/2 raised to the M. This gets another typo. M about that. Got to match my variables. Hello. Raised to the 0 power, 40. Got it. 40 times 1/2 raised to the first power, 20. What if I can copy and paste? Can I? Yeah. Raised to the second power, 10. I'm going to copy and paste again. Raised to the third power, 5. Okay, so look, it's half, 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 half. All right. So this will be 5. Half of 5 is 2.5. Half of that is 1 1/4. Okay. Fill in the tables, then graph the values. This one is decaying. It's going down by a constant multiplier every year. So it's decay. Right on. Let's just do it real fast. I think that graph is going to come down then because it's half every time. So this is going to be months. And the vertical or up and down, that is going to be the price in dollars, I'm assuming. I don't, whatever. It doesn't say what it's in. Could be anything. Pesos, euros, whatever. Rubles, yen. Is the price, well, I still did not graph it. Look at me, moving on. Gotta follow instructions here. And I didn't include a scale. It goes 0, 1, 2, 3, 4, 5. I almost wish that I had moved this over here. Totally going to. White out. We all make mistakes. Just what we do with them that changes the outcome. Okay, so this is still price, but now I put it over there because everything is positive. So why not? What do we want to count by? So that's my next question. Months only goes up to 5, so I can go 1, 2, 3, 4, 5. And this goes up to 40. 2, 4, 6, 8, 10. Yeah, sure. 10, 12, 14, 16, 18, 20. So I'm not going to be able to get in the 40, but that's all right. So 0, 40 will be up here. 1, 20. 1, 20. 2, 10. 3, 2, 4, 5 up. 4 to the right, 2.5 up. Remember, I'm counting by 2s on this scale, and 1.5 up, but that's 2 up, so ish. Okay. And 240. How far up would that be? Okay. There. So here is the slide I see. It's coming down. It's decay. Price is coming down. All right. Is the price growing or decaying? Yeah, my friend. I don't know why I said that. I take that back. I don't know. You're a student. The price is decaying. It is going down every month that passes. Got it. Check. Explain what the 40 from the equation means in the context of this situation. Oh, well, when it just comes on the market, it's the initial price of this game. So the initial price of the game is $40, and that's right here. Initial price up there. Okay, explain what the 1/2 means in the context of, so here's the 40. So there's the initial price. And now we're looking at this piece. Explain what the 1/2 means. So every month that passes, each month, the price drops by, or two, maybe it's better if I say two, half of what it was the previous month. Yeah. What will happen if the input value is increased from 20 to 21? It'll be half the price. So it's just 1 month. So in that 1 month, the price will be half. Half of what it was in month 20. It is becoming very, very cheap. What will happen if the input value is increased from 6 to 8? If the input, I guess, this is right. I guess that is the months, 2 months. In those 2 months, the price drops to a quarter, because it would be half of a half, to a quarter of what it was in month 6. Okay, fill in the blanks just because of this notation. So remember, I just want us to remember what this means. What is the price? Find P when, and look inside here. Is the M. So this is giving us P for price, given a specific M. So when I translate this, when M equals 1, that is the translation of this notation. It's not P times 1. It is find the price when 1 month has gone by. Okay, the price when 1 month has gone by is $20. Find the price when 2 months have gone by. $10. Find the price when, oh, wait a minute. Find when the price is $2.50. So just to make it clear, okay, right there, at 4 months. Okay, just so that I could put in that extra notation. So in this section, right, we wrote some equations for scenarios that are exponential. They have a constant ratio, or I like to call it a constant multiplier, and a different initial value that is separate from that constant multiplier, because the constant ratio is the pattern and the initial is where that pattern started. Describe what the solution means in the context. Yes, so in terms of the price, or in terms of the bacteria, or in terms of the what other caffeine in your bloodstream. Graph exponential growth and decay functions, so plot points. Create an equation, bet, that is y equals a times b to the x exponent, and use a graph to predict some values of exponential functions. So I do kind of want to talk about that a little bit, just real quick before completing this video. You know what? I'll put it in the next video for the next section.